Hi, I'm Dr. Arthur Brodsky, Assistant Director of Scientific Content at the Cancer Research Institute. And today I'm grateful to be joined by Dr. Peter Fecci, a CRI Lloyd Star at Duke University. Welcome, Dr. Fecci.
Thanks, really appreciate it and happy to be here.
So your CRI Lloyd Star work is focusing on the relationship between the brain and the immune system, particularly in the context of cancer. But the brain is a really unique organ and is shielded from the rest of our circulation by the blood-brain barrier, which also appears to make the brain what we call, immune privileged. So what does it mean that the brain is immune privileged, and how does it influence the immune system's ability to recognize and respond against cancers in the brain, both naturally and in the context of immunotherapy?
Yeah, that's a great question, and it is definitely something that folks who are treating cancer in other parts of the body don't always have to deal with. And obviously, cancer is a tough enough problem that adding some of these other elements specific to the brain makes it a little bit more challenging for those of us that work with cancers in this organ. The biggest thing when we talk about immune privilege is kind of saying that the brain is somewhat shielded from the immune system. And part of it is because the brain in general shields itself from a lot of compounds. And evolutionarily, it makes a lot of sense when you think about it. You don't want everything in the world that travels in your bloodstream to be able to just simply get to your brain because it could be devastating. So the way that's set up is that there are these barriers kind of between the blood vessels and the parenchyma, or the main tissues of the brain, that we refer to as the blood-brain barrier. And there are essentially these kind of tight junctions in the cellular walls that make up the boundaries of the blood vessels. And importantly, they don't let a lot of things through. Unfortunately, that can mean that a lot of drugs that we might want to get to the brain don't get there. And it can also mean that the immune system doesn't have as much access as we might like from a cancer perspective. And if you develop an injury in the brain, that can be advantageous because you don't get an overwhelming inflammatory response there that can be damaging. But from our perspective in the cancer world, and particularly in cancer immunotherapy world, we want the immune system to get there. So I think a couple of things, we use the word immune privilege, but I think as time has gone by, we've realized that that's a bit outdated. And really, we describe the brain as more immunodistinct, meaning that actually there is access of the immune system to the brain. We just didn't necessarily know as much about how the immune system worked in the brain, with the exception of kind of learning a lot more in the last, say, 5 to 10 years. And so we've uncovered more and more about how the immune system does gain access to the brain through kind of back channels, if you will. And as we've learned more of that, we know that we can take advantage of more of that as we design our therapies. And importantly, even though there are issues and there are differences in the way the immune system accesses the brain and treats the brain, we understand that things like activated T cells, which are the part of the immune system that we want to get to the brain, actually do have access. And so we can focus a lot more now on manipulating the things that we do understand rather than fearing that the case is dire, which it's certainly not.
That's good to hear. So it sounds like, I guess, to me that it's not necessarily that the brain is shut off from the immune system as much as there's a different way that it interacts, so that they still get in there, but they're not necessarily doing it through the same mechanisms.
Correct. But for years, we didn't recognize that. And so it was easy to just say that the immune system there didn't have access. We understand more now that that's not quite the case, but we still have to treat it differently when we design our therapies.
So with respect to therapies, especially, I guess the two that come to mind, I guess, would be checkpoint immunotherapies, which act on the T cells indirectly, or act on the T cells, and then CAR T cells, which supply actual T cells. So how would, because of this, it's a distinct immune nature, how does that affect the ability of immunotherapy to help patients?
Yeah, also a great question. So there are big differences between the way checkpoint blockade therapy and the way CAR T cells, which are another popular immunotherapy, work. And I think you highlighted one of the biggest distinctions, which is that checkpoint blockade is an antibody that's meant to essentially take the brakes off of T cells that your body already has and allow them to become better activated and to allow that activation to persist. But it does rely on those T cells then being effective at getting to tumor and combating the tumor once arriving. CAR T cell strategies bypass the traditional mechanism by which T cells kill tumors. which normally recognizes the way I describe this is that every cell in the body puts up essentially a flagpole on it and waves a flag saying, here's what's going on inside of me. And that flagpole is something that we call MHC. And to the immune system, which goes around and looks at the various flags that cells put up, it will say, that flag doesn't look quite right. That's not supposed to be here, and it may destroy the cell. And that's kind of the basis for how anti-tumor immunity works. But T cells require those flagpoles to be up in order to work. And if the tumor cells can then counter that by removing flagpoles, which they often do, and the scientific term for that would be down-regulating MHC molecules on their surface, then those tumor cells that do so become invisible to T cells. So what CAR T cells do is they change T cells into a different type of immune cell in a way. They still have the capacity to kill cells, but instead of recognizing flagpoles, they become able to recognize just anything that's sitting on the surface of T cells that might be foreign. And so that bypasses the ability of tumor cells to escape by downregulating MHC or by removing those flagpoles. In the case of the brain specifically, the issue with checkpoint blockade therapy is that, first off, as we talked about, T cells have a little bit more limited access to the brain. So we have to kind of think about that when we design therapies. Number two is that checkpoint blockade antibodies are antibodies themselves, and antibodies don't tend to make it into the brain very well because of that immunodistinct nature we talked about. Now, it's not 100% clear that checkpoint blockade antibodies actually have to make it to the brain to be effective. It's feasible that they just need to bind T cells wherever they are in the periphery, and that will be sufficient to activate them in a way that allows them to traffic in and out of the brain already activated. But that's a little bit less clear, and it's actually a question worth investigating over time. I think the larger issue for checkpoint blockade therapy with brain tumors is that brain tumors are a little bit what we call immunologically cold, which is to say that most papers or most literature suggests that immune checkpoint blockade works better when the tumor has lots and lots of mutations. And the reason is that those mutations give rise to novel proteins that are essentially foreign to the immune system. So the more mutations you have, the more foreign proteins you produce, if you will, and the better the immune system is at surveilling against those, recognizing them, and killing cells that express them. Unfortunately, brain tumors don't have a ton of mutations in them. And so there's fewer of those types of novel proteins for the immune system to recognize and attack. And that becomes true, honestly, whether you're employing CAR T cell therapies or checkpoint blockade therapies. The other issue for checkpoint blockade therapies, and more so actually for CAR T cell therapies, is that if you take any given tumor, and glioblastoma, which is the most malignant brain tumor, is probably the best example of this that we have. These cells are very heterogeneous, meaning that the tumor itself is 1,000 different tumors. Every cell in the tumor is a little bit different than the cell next to it. So even though you want to call it one disease, every person's individual tumor is different than another person's. And even within an individual person's tumor, one section of that tumor is different than another. And even within a given section, every cell in that section is different from each other. And that makes it very hard if you're trying to design a therapy that's targeting a specific protein or target, because every particular cell has a different range of proteins or targets that it expresses. And if you're only targeting one antigen or one target, which is unfortunately very common for immunotherapies, you're kind of already behind the 8 ball before you even begin. So some of the issues really limiting the efficacy of these therapies range all the way from immune access to, once you get there, finding out that your tumor is lots and lots of different tumors that are hard then to combat with a single front. And then the last part of that, unfortunately, is that brain tumors in particular are really, really good at essentially throwing chafe to the immune system. And they are some of the most immunosuppressive tumors out there, despite the fact that they don't really metastasize outside the brain. And even though they're kind of shielded from the immune system, they spend a lot of their energy finding ways to downregulate or sabotage the immune system that might arrive there. So we spend a lot of our energy trying to catalog and understand all the types of immune dysfunction that these cancers and others can induce, and then trying to understand mechanistically how that happens so that we can design novel approaches that take that ability away from the tumors.
That was a great overview of kind of all the different things that can go wrong within the relationship between the brain cancer and the immune system that could allow it to keep surviving. So as you just mentioned, as a CRI star, you're exploring all these different causes of immune dysfunction within the brain, hopefully to shed light on why these cancers don't usually respond well to immunotherapy. So what are some of the most important outstanding questions in this area? And how might your work help us overcome some of the current limitations of cancer immunotherapy and improve care for patients with brain cancer?
Yeah, certainly, my group's not unique in the fact that we study immune dysfunction in cancer, and even not particularly unique in the fact that we study that in brain tumors specifically, although obviously, as you can imagine, there's fewer of us doing that. But I think we've made some important discoveries with regards to some of the immune dysfunction that we see that's somewhat germane to brain tumors or specific to brain tumors and not necessarily prevalent in other cancers. So I would say I'd divide this into two areas. So there are some things that brain tumors do that other cancers do, but that brain tumors just seem to do more of. In other words, they elicit more immune dysfunction than other tumors that might otherwise be comparable. And so understanding how that's the case is important to us, and I'll talk about that more in a second. But the other thing is that there's actually some forms of immune dysfunction that brain tumors elicit that we've not seen in other cancers that are situated outside the brain. And it's important to say that those don't necessarily even need to be brain cancers. Those can also be things like lung cancer, melanoma, breast cancer that commonly metastasize to the brain. And we've found that when those tumors show up in the brain, they now suddenly are able to essentially elicit the same types of immune dysfunction that brain cancers that start in the brain are able to. And probably the reason that is that because the brain has some unique capacities to keep the immune system out and at bay to protect itself. And so tumors that show up in the brain are probably availing themselves of some of those protective mechanisms that the brain has in order to shield themselves in the same way. And when you think about that, if you want to assign a kind of a personality to tumors, it's actually fairly clever. And you have to respect their ability to make use of things like that in order to sidestep immunity. So from our perspective, we've done a lot of work to kind of categorize T cell dysfunction in particular in the setting of cancers, and again, especially in the setting of brain tumors. And we've noted, along with some of the basic immunologists, that basically there's 5 or so different types of T cell dysfunction that can arise. And for years, people didn't categorize it. So if you don't, it's very hard to understand how it's arising and combat it. So one of the really important things that we've done is be very, very, I'd say, kind of structured and careful and organized in the way we divide up T cell dysfunction so that we can approach it appropriately. And some of the things we've noted is that there are some things that we see in lots of cancers, like T cell exhaustion, for instance, which is kind of what it sounds like. If you can imagine T cells getting overactivated or activated for a long time, those T cells can eventually tire out. And so it's not just enough to get T cells to the tumor. You've got to then combat the mechanisms that tumors have for turning off those immune responses even once they arrive. And in exhaustion in particular is one of those that tumors are particularly good at eliciting. And it's one of the major factors limiting immune checkpoint blockade in particular. And we've done a lot to kind of highlight how severe T cell exhaustion is in the brain, in particular in the setting of brain tumors. And we've begun to understand a bit more about how brain tumors and tumors in general actually cause T cells to become exhausted. And what we found is that some of that is different than how T cells become exhausted in other types of disease states like viral infection, for instance. So we're very interested in understanding that. And we've also found some novel forms of immune dysfunction that brain tumors elicit, like we just talked about, this mechanism for keeping T cells out. And what we've found is that any tumor that we find in the brain develops the capacity to sequester T cells away or trap them in other immune organs like the bone marrow. And the reason that's important is because if those T cells are trapped there, then they can't get to the tumor to perform their job. So we've spent a lot understanding kind of mechanistically how that arises. And where we've really had some success in particular is in our quest to try to find ways to reverse that. And when we do it by genetically manipulating mice, for instance, we find that freed T cells, if we get those T cells out of the marrow, are now able to perform better when immunotherapies are delivered to mice with brain tumors. But as we've tried to develop a drug that can do that for us, rather than just having to genetically manipulate mice, we want a drug that we can take to people. We've partnered up with a Nobel laureate down at Duke named Bob Lefkowitz. Our research is particularly relevant to an area that he's an expert in. And so we have a mutual interest in trying to find drugs that can combat this particular phenomenon. And in our quest to find those drugs, we've luckily found that we got more than we bargained for, in the sense that as we've tried to target a particular protein that is relevant to T cells being trapped, we found that when we target that particular protein, we get a lot more than just freeing T cells. We dramatically improve immune cell function and other anti-cancer functions, such that simply targeting one molecule is enough to cause long-term survival in mice in which you put just about any cancer in, no matter where we put it. And so as you can imagine, and that is a really active area for us, and we're in the process of developing drugs, as none currently exist, that target this molecule. And the hope is in the next few years to have this be something that we can bring to clinical trials in patients.
That's wonderful to hear that your work may not only help brain cancer patients, also, as you mentioned, cancers like lung cancer and breast cancer, which are much more common and also metastasize to the brain. So it could also help provide insights that could help those patients. But as you mentioned, also some of these insights into the immune system and immune dysfunction in particular might be applicable to other cancers, which would be great.
That's
So as you're going about on this path, what are the biggest challenges with respect to answering these most pressing questions? And are there any technological challenges that you're addressing at the same time in order to uncover those answers?
Yeah, so I think one of the challenges that we mentioned is trying to figure out how some of these issues for us arise mechanistically. In other words, how does exhaustion arise? What are the underpinnings of this T cell sequestration we're talking about? How do tumors do that? Because to some degree, we're combating things that have already arisen as immune dysfunction. But what if we could instead target the tumor's ability to do that in the first place, so that we never had to combat it at all? We simply just delivered therapies into a context where that immune dysfunction never arose. So that's obviously something that we're very interested in overcoming, but it is a challenge. And that's where we spend a lot of our research efforts focused. I think that, in order to understand some of those mechanistic underpinnings, we do a lot of our work in mice, of course, but it would be relevant to be able to study a lot of these phenomena in patients, as well as how those phenomena respond to interventions we might deliver. The trick is, in order to do that, you really need tumor samples. And it's really difficult to biopsy a brain tumor as part of a research study, right? You need to do that as it pertains to the clinical care of a patient, and people don't tend to just sign up for that. So it becomes really difficult to get there and see how various interventions may be helping things along in patients as we deliver interventions. And so that's why we're kind of relegated to mice or to other animal models. So that is definitely one challenge, and it makes it a little bit trickier to understand what impact we may be having in patients when we begin clinical trials and things like that. I think the other big challenge that we face is tumor heterogeneity. And we talked about that a little bit before, which is to say that, again, we're not just fighting one tumor, even in an individual person. We're often fighting thousands or even millions of tumors. And so how do you do that? Well, how can you become better at that? And I think a lot of that requires thinking outside the box, which is to say, what's the traditional mode through which we target cancers? And to date, it's been targeting protein antigens, and that's what the immune system is meant to recognize. And if we have all these cells in the tumor that are all expressing very different libraries or profiles of proteins, then it becomes challenging to make the immune system work the way we'd like it to. So we've been taking a step back and saying, all right, maybe the traditional paradigm of going after protein targets here is not going to work for us, and particularly not going to work for us in the brain with very heterogeneous tumors. So we've tried to say, what else can the immune system target here that may not be subject to the same types of heterogeneity and the same types of limits? And we've noted that in order to be identifiable as a cancer must do other things that's different than simply express different proteins. And there are a lot of things, as it turns out. And some of those things are the fact that tumor cells may lose the ability to regulate various components and features of their cell membrane, which is the kind of envelope that surrounds the cell, if you will. And so we have found actually that we can find components of the cell membrane that are dysregulated specifically in cancer cells in a way that readily identifies them as cancer cells and that is not subject to the same types of heterogeneity as protein antigen expression is. And even more exciting than that, when we deliver traditional therapies like chemotherapies or radiation, it actually induces more of this disruption so that it's even more prominent in the cancer cells, which means that the technologies that we're deriving that target this type of cell membrane disruption actually synergize nicely with the kind of standard of care regimens that people are getting. So we've begun to test a novel platform that we call Castle, and it's kind of an alternative to a CAR T cell platform. But we've begun to test that and technologies based off of that now in mice with really, really good success. And the hope is that if we can start seeing the in vivo effects that we'd like, in other words, start seeing it cure tumors in the way we hope to in mice, that we may be able to translate that to the clinic as well.
So you mentioned thinking outside the box and how it's going to take kind of new and innovative and creative approaches to really help more cancer patients, which kind of dovetails nicely with the STAR funding, the CRI STAR funding program, which aims to support high risk, high reward research. So why is this CRI STAR funding so important for you? And what will this support enable you to pursue that you might not have been able to pursue otherwise?
Yeah, I think this is an invaluable source of funding for folks in my position. For a couple of reasons. One is it's ample funding, right? So, there are a lot of small funds that you can get out there that might support the first couple of months of a project, but that doesn't leave you kind of with the real flexibility to continue to pursue those endeavors. So again, number one, it's an ample amount of money. Number two is it's flexible, and that's something that traditionally NIH grants or other funding organizations are not as flexible because the money has to be tied very specifically to projects that were outlined in advance. And as a result, as things shift and priorities shift or new data come up, it's a bit challenging to be able to shift gears without essentially constantly applying for amendments or changes to how you're going to apply the money. And certainly we all understand why funds have to be regulated. But for people who have these kinds of novel, quick ideas where they want to be able to at least pursue them and see if they're going to take off, things that are disruptive to the field, for instance, that requires a group that has ample funds on its own to be able to do, which not a lot of research groups have, frankly. So to have large amounts of flexible money that can be used at the discretion of the investigator is a game changer because it allows us to pursue these types of kind of higher risk, higher reward science, as you were talking about, and to be able to decide without having to ask permission every step along the way how funds should be allocated. That provides a lot of trust in the researcher, and I feel most people respond well to that type of trust and feel the responsibility to use the money accordingly, but also to essentially pursue some areas that don't have funding yet because there isn't enough money based on the data we've already generated to kind of apply for larger grants. So I think it really is a great seed funding for a couple of higher reward projects. And I think the CRI does a fantastic job of investigating people who that type of investment might be worthwhile in. Lastly, I think the other reason that it's going to be helpful for us in particular is that there are certain types of things that are not attractive to the NIH or other organizations to fund, things like beginning clinical trials, or in our case, we want to do some IND enabling studies to get some of our drugs from being screened to being ready for clinical trial. And those are areas that are expensive, to bring a drug to clinical trial. And it's hard to get outside funding. So flexible funds are the types of things that really can help actually make that feasible where it might not before. And in our particular case, where we have some things that we'd like to get across the finish line, this may really permit us to do that in a way that would be difficult otherwise.
I'm really glad to hear you mention, in particular, the trust between the researchers, especially in science, where it's literally going into the unknown. You don't know which direction the data or the science is going to take you, and to have that flexibility to be able to pivot, you can kind of follow the discoveries wherever they might lead you.
Yeah, and that's exactly what it is the feeling that I know that as the data shift or the results sometimes reveal something new and interesting, we can immediately shift gears and pursue it rather than to have to take months off and wait for permission to do something. And that, I think, the key there becomes, like you said, trusting that you've got an investigator who you think is going to make those types of snap and important and correct judgments. And I think that's really the flexibility that this type of funding provides.
So what do you hope to accomplish over the next 5 years or as a CRI star? And how do you hope that your work will impact the field overall?
Well, I'd love to say cure cancer, but that might be a little over optimistic for 5 years. I do think we can make substantial headway. And what I'd really like to see are two things. I'd like to see us truly understand the mechanism of some novel findings that we've had, because if we do that, then we'll identify novel targets in cancer, which can be the source of entirely new drugs and new classes of drugs. And that's kind of what we did with the BAR2 inhibitor that I talked about before, although I didn't mention it by name, but this drug that we're working on with our Nobel laureate colleague. And I think that the capacity to do that now with this funding means that I can expect that we'll be able to take that drug across the finish line and in the next 5 years have it in clinical trials and actually have a chance to see what impact it's going to have on patients with cancer directly.
Awesome. So thank you very much for taking the time to speak with me today. And I can't wait to follow your work. Best of luck.
Really appreciate it. And I hope this was helpful and interesting for the folks that are watching.
Thank you.